Hello, this is a video on relative velocity and relative acceleration analysis in Chapter 5 of MSD210. I'm going to start with a problem from Chapter 5, 580. This problem was in the homework assignment, I think homework 3. And I always start by drawing a picture of the problem. This helps me to understand the problem, to make sure I've read through all the details and I've understood everything that's being asked. So here I have a link OA. Here I have a link BD. Here I have the plate P. We are told that this length is 0.2 meters. This length is 0.2 meters. I haven't drawn it very well to scale because we're also told that the length of BD is 0.5 meters. So then this length is going to be 0.3 meters. The length of OA is 0.6 meters. So this length is 0.4 meters. Okay, I just want to start quickly thinking about the geometry. It's always helpful to think about the geometry of these problems. This length is 0.3 meters, this length is 0.4 meters. We can define this angle here as theta. Now, interestingly, this is a special triangle. If I want to work out this length, it's going to be the square root of 0.3 squared plus 0.4 squared. And that is a special triangle, the 3, 4, 5 triangle. It ends up being 0.5 meters long. So I don't need to work out the angle theta because I can read off this triangle that sine theta will be 0.3 over 0.5 and cosine theta will be 0.4 over 0.5, which is 4 over 5. Okay, we are told that these two links, OA and BD, cross each other but don't touch each other. So they can move relative to each other like this. This plate P has an angular velocity, omega P equals 2 radians per second. And we are asked to determine omega OA and omega BC, the angular velocity of the two links. We're going to do this problem using the relative velocity equation. VA equals VB plus VA relative to B. And so the first thing to do in starting to understand this problem is make sure we understand what direction these velocities are. What is the velocity of point A? Well, I know that point A is connected rigidly to point O. So point A can only move in a circle around point O. It is constrained by the rigid connection to move in a circle around point O. Instantaneously, that means that point A's motion must be horizontal. At this stage in the problem, I don't know if point A is moving to the left or to the right, but I do know that it must move horizontally. When I come and look at point B is constrained to move in a circle around point D because it's connected to point D by a rigid link. So that instantaneously it is moving perpendicular to link BD. Now we come to this VA relative to B. What exactly is the meaning of VA relative to B? If we come and take this link AB. So first of all, A and B are connected to each other by this rigid plate, which is called P. But the plate moves as a whole, so they could as well just be connected by a link. The shape of the link doesn't matter. So we can think about it just as a link AB. When I think about the velocity of A relative to B, I take that link out of the system and I pretend that point B is fixed. Point B does not move. Then we see that point A is moving relative to point B in a circle around B, perpendicular to this link. Okay, that's very strange. How can B be fixed? We know that B is not fixed, but this is not in reality, this is measured as if. So I imagine shrinking myself down to the size of an ant, sitting there on point B, and looking at where point A can move relative to me. So we know that point B is moving, but measured by a person sitting on point B, A is moving in a circle. A can never get closer or further apart. It's only moving in a circle around B, measured from point B. So that's the idea of VA relative to B. Now notice that if I want V of B relative to A, then I will fix point A, V of B relative to A, will be in a circle around A. The second thing is that we know omega P. We've been told that the plate has an angular velocity of 2 radians per second. So what does that mean about omega AB? Omega AB must be equal to omega P, because omega AB are 2 points on the same rigid body. All lines on the same rigid body have the same angular velocity and the same angular acceleration. So I know that omega AB is counterclockwise. So that means that relative to B, A is moving in this direction. Relative to A, B is moving in this direction. We can see from this that V of A relative to B is equal and opposite to V of B relative to A. Okay, so if I come back to my original drawing and I sketch on there, I want V of A relative to B. That is going to be in this direction. And it's going to be perpendicular to the link AB. Now, when I want to draw this onto my velocity diagram, I want an angle. I've already defined this angle as theta. This angle here is 90 minus theta, so this angle here must be theta. V of A relative to B is at an angle theta below the horizontal. Okay. Now I want to draw the velocity diagram. Let me rewrite this equation. V of A equals V of B plus V of A relative to B. So this equation tells a story. It says there are two paths, this red path and this green path. Both paths start in the same place and end at the same place, but they take different routes to get there. This is as if you and your friend leave class and agree to meet at the piazza for lunch. One of you walks straight from class to the piazza, the other one has to walk via an ATM to get money, and so you take two different paths. You walk from the same place to the same place, but you walk on different paths to get there. So let's identify what we know and what we don't know in this equation. We know the direction of VA. We know it's horizontal. We don't know the magnitude. We know the direction of VB. We know it's vertical, but we don't know the magnitude. VA relative to B, because we know omega AB, we know the direction and the magnitude. So we know both of those things. So we start by drawing the one that we know two things of. So now, just before I move on, there are two unknowns in this equation. It's a vector equation in 2 dimensions, so there are 2 equations. So I can solve for these 2 unknowns with these 2 components of the vector equation. So I start by drawing the component I know. I like to draw a big dot for the tail of the vector. There's VA relative to B at an angle of theta below the horizontal. I don't guess these angles, I draw them on the original geometry, and then I copy them over. Now, V of A relative to B plus V of B. So with a tail here at the head of VA relative to B, and vertical, but we don't know if it's going to go up or down. This is the line that represents the possible direction of VB. That's the green path. We start there, we walk here, and then either we're going to walk up or down. The red path must start in the same place, and we know that it must be horizontal. So the only way to close this diagram, close this triangle for these 2 paths to meet up, is in this direction. Okay, now I have a completed geometry, vector geometry of the problem. And I can read off from this. If I redraw my labels, now I know where they must go. V of A over V of A relative to B is cosine theta, which I've already worked out is 4 over 5. V of B over V of A relative to B is sine theta, which I've already worked out is 3 over 5. So I can work out V of A relative to B and solve for these. So this is the geometry method of solving relative velocity problems. Now we're going to come and try the algebra method. I always like to start the problem by sketching the geometry, but sometimes when we come to solve it, it makes more sense to use the algebra. I want to encourage you to do it both ways. Try it the way that you're more comfortable with first, and then go back and repeat the problems you've already done with the other method. So if you like the geometry method, solve the problem using geometry, and then when you're doing homework problems in practice, repeat it using the algebra method. Or if you like the algebra method, go back and repeat it using the geometry method. If you learn how to use both methods, it'll give you better understanding of how these problems work. When we come to solve this problem using algebra, we say VA equals omega OA cross R of A relative to O. This is very important. R of A relative to O is a vector pointing from O to A. This notation, A relative to O, means A measured from O. Okay, so this vector, and this is the notation we will use throughout this class, always points from the second letter to the first letter. This is the opposite direction to how you defined vectors in SWK. You need to get familiar with this. We will use it consistently. If you don't get the position vector wrong, you will get many other things wrong in the problem. So, I don't know the magnitude of omega OA, but I know that it is in the k direction, either positive k or negative k. So I can write an unknown magnitude with a known direction k, crossed with R A relative to O. So from O to A is 0.6 J. And this tells me minus 0.6 omega OA I. It's very helpful to remember the IJK triangle. Going around IJK is positive. K crossed with J is in the negative direction. K crossed with J gives us negative I. If you forget it, you can always just draw this on the corner of your page. So VA equals minus 0.6 omega OA I. Notice that this is exactly the same. This is an algebraic expression of this equation. It says VA is moving in the I direction. We don't know until we know the sign of omega OA, whether it's moving in the positive I or the negative I direction. We do the same thing for VB. VB equals omega BD crossed with R B relative to D. So that's an unknown magnitude in a known direction, omega BD K, crossed with from D to B 0.5 in the positive I direction. So that gives us 0.5 omega BD. K crossed with I is positive J. Finally, and this is exactly what we've drawn on this picture, we've said VB is in the J direction. We don't know until we know the sign of omega BD whether it's in the positive or the negative J direction. Finally, VA relative to B equals omega AB crossed with RA relative to B. Omega AB I know is 2 and it's counterclockwise, which is positive K. RAB points from B to A, negative 0.3 I plus 0.4 J. So that works out to be K crossed with J gives us negative I, negative 0.8 I. K crossed with I gives us J minus 0.6 J meters per second. This is this vector. This is the mathematical expression of this vector, which we've also drawn here in this velocity diagram. So in the geometry, we've drawn the magnitude for VAB. We know the magnitude and direction. We've said VB must be vertical, VA must be horizontal. Somehow we must join them up. Let's do the maths to join them up. I'm just going to cover over this picture now. So when I substitute each of these three things, three expressions, into the relative velocity equation, we find minus 0.6 omega OAI equals 0.5 omega BDJ minus 0.8 I minus 0.6 J. Okay, now we solve this equation by grouping I and J components. Because this is a vector equation, the coefficients of I must independently satisfy the equality, and the coefficients of J must independently satisfy the equality. We can also see that you can group I and J if you take this equation and take the dot product of the whole equation with I. We dot product this with I, we get minus 0.6 omega OA. Dot product this with I, j crossed with I is 0. We dot product this with I crossed with I is 1, minus 0.8. Dot product this with I, we get 0. J components, 0 equals 0.5 omega BD minus 0.6. So I get two equations in two unknowns. In this case, the equations are very simple. I don't need to solve simultaneously. We find omega OA equals 0.8 over 0.6, which is 4 over 3 radians per second. I started out by assuming omega OA was positive counterclockwise. I have found it is positive, so that's counterclockwise. We get omega BD equals 0.6 over 0.5, also counterclockwise. Does this agree with what I've drawn here? VA we found to be moving leftward, which corresponds to a counterclockwise motion of omega OA. VB we found to be moving up, which also corresponds to a counterclockwise motion of omega BD. So that's the geometry and the algebra are in agreement.